think we can start this morning session. And it is a pleasure to this Abel Klein, first speaker for today. And here is the title, An Eigensystem Approach to Anderson Localization.
Okay, thank you very much. This is joint work with Alex Elgart. This is the first of two talks. Alex will give the second. In this talk, I'm going to give an overview of what we did, and in the second talk, Alex will go into some of the details. So I basically want to present to you a map of what you have done. First of all, we'll work with the simplest possible random triangle operator. That's the Anderson model, which I'll write like minus the Laplacian plus v omega. I have the center discrete Laplacian, standard one. V omega is omega x, whereas the omega of x's are independent, identically distributed random variables. Of course, non-degenerate probability distribution mu will take with bounded support for convenience. And that assumption will take mu to be Holder continuous with order alpha bigger than a half. Of course, that means that if I look at the concentration function of the measure, which is given here, S mu of t is bounded by a constant k t to the alpha. You just have enough to do it for a bounded t. And if alpha equals 1, that's the usual hypothesis that mu has a density, a bounded density. But it doesn't make much difference for what we do to take alpha bigger than a half, so we are going to do it. And of course, the way I'm writing epsilon is the inverse of the usual disorder parameter. Usually write minus Laplacian plus v omega, but here is more convenient to write it in this form. So 1 over epsilon is actually the disorder. You recall that the spectrum of this operator is actually non-random with probability 1, and for this particular operator, you actually know what it is. It's the interval minus 2d epsilon to 2d epsilon plus the support of mu. So you take a point here, take all those sums, and this is 2 is probability 1, and we will consider epsilon small. Okay? Now, very briefly, let me introduce some notation. We'll work with the maximum norm, so sup norm. So norm of x will be the maximum of absolute value of the coordinates. Occasionally, we use the Euclidean norm. The distance and the diameter of a subset of Rd are going to be calculated with respect to this norm. That's one thing I want to say. We are going to consider Zd as a subset of Rd because for convenience, we use boxes in Zd that actually centered a point in Rd. So what I really mean is that for me, a box in Zd is a box in Rd intersected with Zd, and the center is in Rd. Does not have to be in Zd. This turns out to be, it's not essential, but it's convenient to simplify some things. And with this, the size of a box, the number of points, is always order L to the D. And also convenience, if phi is containing theta, containing Zd, I always consider L2 of phi to be a subset of L2 of theta by simply extending all functions on phi to be 0 outside phi. And the norm of phi is the L2 norm, and occasionally may use the sup norm. And we use simple boundary condition. If I take an operator, an L2 of Zd, and a subset, by k theta just means I take the restriction of k to theta and consider it as an operator in L2 of theta. So just cut the bounds that connect theta to the outside, and that as a boundary condition. Okay. Now, the object we are going to work with is what I'm going to call eigenpairs and eigensystems. So let me consider not a random operator, just a fixed operator of the form you are interested, minus epsilon Laplacian plus v, and consider a subset. Now we are going to call phi lambda an eigenpair for h theta if lambda is an eigenvalue and phi is a normalized eigenfunction. So that's the usual thing. It's just easier to say eigenpair to keep on saying I have an eigenvalue and a normalized eigenfunction. So that's an eigenpair, the usual thing. And a collection of eigenpairs we call an eigensystem if they actually phi of j is an orthonormal basis for L2 of theta. So basically if they are diagonalized h of theta. So eigensystems just mean I have a complete system. And trivial observation, if theta is finite, so all eigenvalues are simple, we have a matrix, a finite matrix, we can rewrite the system as being indexed by the points in the spectrum because they are all distinct. So every eigensystem then can be rewritten as phi lambda lambda, and lambda is a point in the spectrum. This is just notation, but it's convenient. Now, I don't want you to remember that. I just want to tell you that to fix those, we have the right relation. We are going to fix numbers zeta, xi, zeta, beta, be less than 1, gamma is bigger than 1. It satisfies a certain relation. I'm going to take tau bigger than this quantity and less than 1. And then I have this whole thing. Now, you can't forget it after that, but what I'm going to say is these relations are used, and I can establish them, and everything works out. So let's forget them for the moment. 1, huh?
11.
Huh? Yeah, I mean, it's okay. Of course, there is a quadratic form here. You realize that's where it comes from. Okay, also I'll need something between zeta and beta. I'll take something in the middle, it's not important, zeta tilde, and just something slightly bigger than tau is smaller than 1. So this is just notation. We fix some, so you don't have to worry, and all relations that we are going to need are going to come from, you can even forget that. This is just to say you can actually build them, so you actually get that. And one more bit of notation. I always have scales capital L and little l related by capital L is little l to the gamma, where gamma is the one that comes here. And one more, because we are working in ZD, this quantity, the floor or the largest integer less than equals than L to the tau is going to appear. I'll simply call L sub tau, so I don't have to worry about it. And basically what you're going to need is that this is much bigger than 1, is much smaller than the other one, and this is much smaller than L. And also this is going to appear, although not explicit, but it's built in. The way these things are done, little l to the tau is perfect. L to the gamma tau is much bigger than L to the beta. This taken for granted from now on.
Oh, wait, leave it for a moment. We will remember it.
You don't have to remember. I told you don't have to remember. I just want you to believe I can get them. When I say things are true, you believe me. That's all the purpose of this slide.
It goes without saying.
Yeah. I know. Okay, so now let me start seeing. Okay, the first definition, let me take a box, a point in the box, and some mass, I'll call it M here. Then a function in literal 2 of the box is said to be xm localized. I'll always assume that I normalize it to 1, and it decays like e to the minus m y minus x for all y here, such that y minus x is bigger than equals than L of tau. But be careful because I am considering boundaries too. So if I take a point here and I take L to the tau here, it decays from here, 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 but nothing happens here. And if you are here, of course, it decays to every point in this boundary. This is just a definition, but that's going to be an important definition for us. what it means for a function to be localized at a point with a certain mass in a box. And the other definition that is going to be, if I fix a positive number r and I take a finite set, I'll call that the finite set is r-level spacing for h. If first all eigenvalues of h of theta are simple, and if I take two eigenvalues, the difference between the eigenvalues is bounded from below by e to the minus r to the beta. Those basically are the two concepts that from which we are going to build everything. Localized eigenfunctions and level spacing in boxes at sets at a level spacing. And if a box, I take a box and it is L level spacing, where L is the length of the box, I will just say the box is level spacing. And those are the two things from which we are going to build everything. There are going to be no Green's functions in this talk, except to say that there are no Green's functions in this talk. Okay? And those are the two key properties that we are going to follow. You know? Okay, so let me now tell you what our really main result. First, I'll define what's going to be a good box in this procedure. So let me fix M positive. I'll call a box lambda L M localizing for H if one, lambda L is level spacing for H, so all the eigenvalues are simple and separated by e to the minus L to the beta. And second, there exists an M localized eigensystem for H lambda L. It means an eigensystem phi x lambda x indexed by the points of the box for the operator restricted to the box, such that this function is xm localized for all x in lambda L. In other words, for me, I say that a box is good if all eigenvalues are localized and around each point there is a function, eigenfunction that is localized around it within cap L to the theta. So that's a definition of a good box for us. I'll call it M localizing box. And now the theorem, that's the main thing we do actually, and everything is going to follow from this. Let me consider an Anderson model. I can find a scale such that if L0 is bigger than that fixed scale, and there exists epsilon 0, doesn't matter what it is, I'm putting an expression here which just tells you that it gets worse and worse with L0 grows, such that if I can take a mass which also has a dependence of this form, which is not really important, then we have that for all boxes of size L, the probability that the box is M localizing for H is big. Big means 1 minus e to the minus L to the chi. And this is true for all scales bigger than L0. Yeah?
Number one, is there something missing in that? Or
No. Lambda L is level spacing for H.
At what scale?
Oh, I said that if I have a box, the scale is the side of the box.
Oh,
Okay, let me go back
so R is L.
here.
Oh, I understand.
Okay, just for convenience, I mean, if it's a box, the box has a scale, so that's the scale we use in the box. So there exists a finite scale such that if you take epsilon, there exists an epsilon 0, and I can write an M which depends in L0 and epsilon, and all these parameters, this exponent I fix, but then for all boxes, the probability that the box is localizing is big, by big mean 1 minus e to the minus L to the chi. And this is true for all scales bigger than L0. That's the main theorem, and I will discuss how we get there. But all it's basically saying is good probability, boxes looks like that. Eigenvalues are separated, and which is somehow your intuitive idea of the best type of localization you could think of, at least in finite volume. I mean, this, of course. Okay, so let me then comment. The motivation comes from many-body localization in the work of David Hughes and others. The usual Green's functions approach do not appear suitable for this problem. New method needs to be developed. John has noted that, and he has an approach which is based in construction approximate eigenfunctions or diagonalizing approximate eigenfunction using perturbation theory, also left side of the box. He's here. He can explain to you what he does. We perform a mood scale analysis based on eigenpairs instead of Green's functions. We hope the technique may be useful in other situations. Of course, the infinite volume localization results for the Anderson model at high disorder are well known. Those have been well known for a very long time. Not claiming anything new here. What's new is our method. And at the moment, the method only works at high disorder. Okay, comparison with the usual mood scale analysis. The usual mood scale analysis is a basic object a Green's function. We do not use Green's function. The basic object in our approach are eigenpairs. The decay of Green's functions is replaced by localization of eigensystems. We have localized eigensystem is the way I have defined. The usual mood scale analysis relies on Wagner's estimate. The one I'm going to present today does not use Wagner's estimate. It uses a probability estimate for level spacing sets that I did with Stas a long time ago using Minami's estimate. I will state it at some point. So there are things I think we can now do without using Minami. We are going to lose in using just Wagner or Wagner between boxes. But we lose a little bit on the labeling, but this is not finished yet, so I'm not going to talk about that. The one I'm talking about that uses an estimate that we derived from Minami, but probably could be derived independently, but we still cannot do it independently. The usual mood scale analysis is done either for a fixed energies or for energies, but with two boxes with for every energy it holds either on this box or on the other box. Our method treats all energies in a single box at once, and we give a complete picture in a fixed box. The probability estimates are the same as in the usual mood scale analysis. I'm not even going to talk about them. They are exactly the same. And I'm going to do it the way they were done in my work with Germany. Now, the labeling, that's really, I think, new in this context. The labeling of eigenpairs is done using Hall's marriage theorem. I'm going to explain that later in the talk, and Alex will do more about it in his talk. That's how we actually are able to attach eigenpairs to sites on the lattice. It's combinatorial theory or assignment theory, as they call it. Okay. Now, let me state, although this is more standard, how we actually get localization from the mood scale analysis statement I had there. So I need some back notation. So we fixed deterministic discrete Schrödinger operator. As usual, we take nu to be something bigger than half the dimension and use this bracket x square root of 1 by the norm of x squared. If A is in ZD, I'll define TA to be the operator on literal 2, which given by multiplication by bracket x minus a to the power nu. You can always switch from one to the other. TA, TB inverse is bounded, and you have a bound. Now, I'll need generalized eigenfunctions. So psi defining theta is a new generalized eigenfunction with generalized eigenvalue lambda, and I'll just say generalized eigenpair. if, first of all, it's non-zero, and second, what I should call the generalized eigenfunction norm is finite, and it satisfies point-wise the eigenvalue equation. But this I mean in the point-wise sense, the eigenvalue equation. And of course, I put 0 here, but because of that, if this is true for 1, it's true for all A. Okay? So it doesn't make any difference which A or all I use here. So that's the usual generalized eigenfunction. And giving lambda, a real number, V of lambda would denote a collection of generalized eigenfunctions with generalized eigenvalue lambda. And if I give you lambda and 2 points A, B, I set W, lambda A of B. I take the value of the generalized eigenfunction at B, absolute value, and divide by generalized eigenfunction normal centered at A. If this is not empty, otherwise it doesn't make sense, and I define to be 0 outside. This is basically definitions I had in work with Germinet some time ago. These are very close. And just a trivial observation, mainly in the lattice for A and B, this quantity is always bounded by R minus B to the nu, so it's always bounded. And if I have A and A, this is always a number less than equals to 1. So we have this uniform, a priori uniform bounds in these quantities. That's one reason they are also convenient. Okay, in terms of this quantity, and that's how we state localization. So I have the generalized eigenfunction divided by each generalized eigenfunction norm. I can change that using this. So what I put here is not quite as important. And I'm taking for a fixed lambda, I take the sup over all possible. So this quantity really depends on lambda, not on the particular generalized eigenfunction. Okay, so this theorem encapsulates localization. So let me consider an Anderson model. Then I can find an epsilon, I can find a scale, and I can find a mass for epsilon less than or equal to 0, such that for all scales L is bigger than L1, this is just for convenience for the statement. It can be done without, just get a bit messier, with L in 2n and A in ZD. I can find an event Y depending on L and depending on A, and this event has the following properties. It depends only on the random variables indexed by points on the box of side 5L at A, and the probability is big is 1 minus some constant to depend on what this is, e to the minus L to the chi. And for all omega in this event Y and all lambda, we have that if I look at this W at lambda, this of course is random, depends on epsilon, but if I look at it at lambda, a lambda, and this is big, and big here, minus 1/4 of ml, see? Then, if I look at the same thing at Y, where Y is in an annulus between something a little bigger than L and less than something a little bigger than 2L, then this one is small. If it gets big here, it has to be small on the annulus. So what I'm really saying is that if you prefer, I'm really taking a box of size 5L, and here is A, and if my eigenfunction is bigger than something here, then if I'm looking at something here, for every point here, this is small. And in particular, using the uniform bound I had before, the product of this at A and the product from this at Y is always bounded by the smaller, which is this one, for all Y in this angle. This gives you localization. This encapsulates localization that I used before. This is not new in the way it works with Germinet. It gives Anderson localization, it gives dynamic localization, it gives Sully, it gives all the usual manifestations of localization. If you fix L0 and you set L, to explain why, just quickly, if you set scales that are just double the scales, then ZD, that's why these A's were defined that way. It's basically the union of these times something that is fixed. Then, if you look at what multi-scale analysis is, the Anderson localization, if you Borel-Cantelli argument, you get pure point spectrum with exponentially decaying eigenfunctions. And if you use a slightly more elaborate Borel-Cantelli argument, you get dynamical localization from the Atlas inequality, which has the product of the two W's. And you can get from this also dynamical localization expectation of exponential decay. None of this is new from that theorem. This we had done before, so I'm not going to spend time on that. But once you have that, you get all the usual statements of localization for the model. Okay. Now, let me tell you what goes into the main theorem. First, I said that I use this probability estimate for level spacing sets, and this was proved with stars. We are actually trying to improve simplicity of eigenvalues for the Anderson model. So, if you take theta in ZD, I an interval, and eta to be a number, small number, between 0 and 1.5, and now consider the event that h theta has at most one eigenvalue in all sub-interval of j's with length less than or equals than eta. Then the probability of this event is bigger than 1 minus, this is a constant, k comes from the probability distribution. This is the length of the interval. Eta is here. Alpha was a Holder exponent for the measure. And this tells you why I need alpha bigger than 1/2. We derive this lemma from Minami's estimate, and if you look what we had, we use this to prove simplicity of the spectrum, and the proof shows simplicity of the spectrum if you have Holder continuity with alpha bigger than 1/2, and the reason is this. And the same here, because we need this estimate. For us, let me translate it for in the way we are going to use it, the same thing. Let theta be in ZD, L in 1, and for all small epsilon, the probability that theta is L level spacing for h is bigger than 1, minus a constant depending epsilon 0, and the constant is actually written what it is here. It depends on the support of the measure. Some of these things can be improved if you want to make more general. It depends on epsilon 0 dimension. This is a constant times e to the minus 2 alpha minus 1 L to the beta times the volume squared. The volume squared reminds you of Minami, and that's where it came from, the way we proved it actually. And in the special case of a box, the probability that a box of side L is level spacing is 1 minus of 1. This is what matters, and this is basically e to the minus a constant L to the beta. And that, so we use it the same way we use the Wagner's estimates in the multiscale analysis. But that replaces the Wagner estimate. The probability that a box, actually we need this one too. You need more general sets than box. You have a probability that a set is level spacing. You have, this happens with good probability, basically controlled by e to the minus L to the beta. Okay. Now that was the theorem I said we prove. And I made just one change. I switched from L0 to L0 to 1 over gamma, so but that to compare with the next one. So there is a finite scale such that if L0 is big enough, I take some epsilon 0 and I can get a certain mass such that the probability that lambda L of x for all x is m localizing for h is bigger than 1 minus L to the chi for all L bigger than L0 to Z gamma. Well, this will be proved by proving what the following proposition, and this is a more standard form of the multiscale analysis, although we have used this before. That says there exists a finite scale such that given L0 bigger than L and setting Lk plus 1 Lk to the power gamma for k 0, 1, and for all epsilon smaller than something, we have that the probability that lambda Lk is m localizing is bigger than 1 minus zeta minus Lk to the zeta for all k where we have this expression. We prove this theorem from this. We lose a little bit. Look like this 1/2 becomes a 1/4. And remember that chi was slightly smaller than zeta. But that's what we prove, and it's basically a simple argument to go from by covering boxes of size L by boxes of sizes Lk to go from here to here. And this is something I used before. Okay. So the proposition itself, as you use a multiscale analysis, there are two things you have to prove. You have to prove you can start a multiscale analysis. That's the initial condition. So let epsilon be positive, L bigger equals 1, set a mass. Then if L is sufficiently large and epsilon is small enough, we have that the probability that this is localized is 1 minus e to the minus L to the zeta. Elgart is going to talk more about that. That is basically done. That's simple to do, you know. If you can do it for high disorder, you can always prove statements like that for the Anderson model. And then the multiscale analysis proper, I mean, what you really have to prove, what most of the work goes, is that you fix epsilon 0 and fix a lower bound on the mass. Then there is some scale such that if some sufficiently large scale and epsilon less than this epsilon 0 and m0 has bigger than this fixed lower bound, this fixed lower bound comes in the constants, we have that if we can establish, which comes from here, that the probability that lambda 0 of x is m0 localizing for h is bigger than 1 minus e minus L0 to the zeta, then setting Lk plus 1, Lk plus gamma, we have that the probability that, and always you lose something, I'm just taking a half, probability that lambda Lk of x is m0 over 2 localizing for h is bigger than 1 minus e to the minus scale over zeta for k equals 0, 1. That's where most of the work goes. This one gives you the starting condition, and putting those together you get the previous one, and then you get, but that's where the work is going to go. So let me tell you how we approach it, since we don't have Green's functions, and that's really what is different here, that we're not using Green's functions, don't have the resolvent identity, and somehow we have to go from a small scale to a bigger scale. And okay, so let me fix that so I can always forget. I need a lower bound for the constant, so I will not write, but lambda L is always a box, and L is always sufficiently large. I'll have several masses that are going to appear, which are always going to be of the form bigger than 1 minus some constant L to some power for some appropriate power, which I'm always also going to ignore in the talk, but you can do everything very carefully. And unfortunately, there are some notation I need. First of all, what do I call psi of theta and t? Well, the points whose distance is bigger than to the outside is bigger than t. So if I have more or less something like that, and if this is t, this is a psi of theta and t, okay? I'm taking everything that's a distance t from the boundary. The t is going to be large, so the fact that I'm taking the floor doesn't make much difference. So I'm taking all the points which are far from the boundary, if you prefer, but the boundary with respect to theta, not with respect to zd. just with respect to theta. And then the external boundary is the usual one, is the Euclidean norm, because here it's used for the Laplacian. Every v that is in theta but not in psi, and it's an Euclidean distance 1, so the Laplacian in ZD would couple them. And the internal boundary is, I'm taking the u in psi that couples to the outside to theta. And this is going to come, I'm going to take the complement of this and add the external boundary. So this other one, when you do the Green's function, usually you only need the internal boundary and the external boundary. But here you need the thicker boundary, which actually doing the continuous too. So what I really mean, so this is t. I'm taking everything here, and then I'm adding these points here, not here, just in the Euclidean norm. Okay? So you have like a thick boundary. That's all that is. Okay, so this is just unfortunate notation, but it's needed. Now, the first lemma that is going to tell you how we are going. Let me take x to be a point in a box, lambda, contained in theta, and suppose phi is xm localized. The eigenfunction, a localized eigenpair with eigenvalue lambda. Then, and that's where these tau's are going to come, because then if I take a box and now I take the inside of the box, but this is now roughly is L to the tau, so this is a box of size L. Well, I'm using capital L here, but doesn't matter. And if x is inside, not too close to the boundary, then the distance from lambda to the spectrum of h theta in the bigger volume, which is smaller than this quantity, is bounded by e to the minus m1, which is m with some correction of size L, L to the tau. So this is, so that means that if I take any point here and I take the eigenfunction localized here, the corresponding eigenvalue is close to an eigenvalue in the bigger box. We don't have the resolvent identity, so those are the sort of things that we are going to have to use for once from a scale to another. And then let's be a generalized eigenpair, and let lambda L be a localizing box with localizing eigensystem, so I have all of those localized eigenfunctions. And suppose I take lambda that is not too close, that is a level spacing, if you remember, not too close to lambda x for all x in the center. I don't care what is happening close to the boundary. I'm just looking what happened in the core of the box. Then the following holds for sufficiently large L. If I am deeper inside, not L to the tau, but 2L to the tau, the value of psi of y is bounded by a small number times psi of for some y that is up here. So whatever is happening, now I take a smaller thing, right? I double it. Anything here is bounded by the values in the boundary. So the values in the thick boundary control what's inside, and we can do better, and that's why you need more than tau. I need tau tilde, which is bigger. If y is actually here, psi of y is bounded by something in this thicker boundary, but here I have decay of the order y2 minus y. This will give localization in the next scale, I mean. If you satisfy this condition, you can move, and as you move, you keep on, you get decay. So this is an important lemma, And this lemma is used to prove what I'm now going to try to state and explain. So let me now. These are preparatory. So I have some theta, which I don't particularly care what it is here, and then I have a box lambda L of A, so here is A, which is contained in it, and this box is good. It's localizing with a localized eigensystem, and I also assume that theta is L level spacing. Since it's level spacing, the eigenvalues are simple, so I have an eigensystem that I can label that way. Okay? So I have a level spacing box, and I have a good box inside that is localizing. So now making statements, the following. That if I take an x in the core of this box, lambda L, with respect to theta, I can map it into an eigenvalue of h theta, such that the differences between the eigenvalue in the small box and the eigenvalue in the bigger volume is small. And if I look at the eigenfunctions, I have to align them. That's what I mean by multiplying by a suitable phase factor. If I align them, the difference in norm is also small. So an eigenpair, that's what really saying that if I am inside this box and I take x and I take the corresponding eigenpair, this is close to an eigenpair in the big box. That's important for us. And second now, let me, for this A, let me call sigma A h theta to be the collection of all these eigenvalues that in the bigger box and the bigger volumes that I got from the eigenvalues in the core of the good box. Then if I take lambda here, we actually have that the corresponding psi of lambda is small outside that box. In other words, if I got an eigenvalue that came from this in the bigger box, the corresponding eigenfunction is small in the rest. It's localized inside that good box to start with. And if lambda now is an eigenvalue, but it doesn't come from the core of the good box, then it's far away, it's far from all the eigenvalues of the good box in the core. And if this is true, the last lemma applies. So I have this and I have this. I have decay. So they are controlled by the boundary. So this statement is saying that the values of the corresponding eigenfunctions in the core of the good box are controlled by the values in the boundary, and I do actually have some decay. And now one more thing, if I happen to have two boxes, lambda A, lambda B, which are both localized and contained in theta, and I take x in one and y in the other, and they are mapped into the same eigenvalue of the bigger volume, the x and y are not too far apart. The norm of x minus y is bounded by 2. This is roughly L to the tau. These are important ingredients to go from one scale to another. Those are the statements that replace the resolvent identity, if you want.
This is true, there's no probability involved here. This is just always true, right?
This is always true. Yeah, those are not. Those are, I have the hypothesis. It's localizing. Yeah, but those are deterministic statements. And the work comes into do that you can get probabilities that allows you to use a deterministic statement. In certain events, you have these conditions, and you can do this. Yeah.
I just I couldn't understand why you would get 4 deterministically.
Huh?
Can you explain how you get 4 deterministically?
Which one?
Number 4.
This one?
Yeah.
Oh, because of this. And because these are decay. Okay. For the following reason. First of all, if this happens, lambda xa and lambda yb have to be close, right?
Yeah.
If they are close, the corresponding eigenfunctions are also close by triangular inequality from here. Okay? And now then, notice the following. Let me put here y, let me put here a. No, yeah. These eigenfunctions are only significant in a box of size 2L theta. So this is L to the theta. Right? Because then they start decaying. So that means that if I am going to get phi tilde of xa minus phi y, not tilde, no tilde here, I'm sorry, phi b of y small, which I get if they are close, that means that those things have to touch. Right? And if they have to touch, and that's the scale, this is L tau, this is L tau, this thing have to touch x. I think I had x here, I'm sorry, I had x, not x minus y has to be less than L to the tau. It's just, it's a construct, it's deterministic. This is just, things were built up that way. Okay, you have to prove you get into this situation because I'm giving you the hypothesis, and from the hypothesis these things follow. But, okay?
Well, this seems to be a variant of argument
Huh?
with Balchan.
Huh?
It's a variant of argument for simplicity in the entire lattice which you made into from 60s.
These things are similar. There is a, we are using the same probability estimate.
On a finite scale.
Yeah, we use some of those things, yeah. Although this is stated in a somewhat different way, but it is a lot, yeah. I mean, just putting things together, all these things are sort of known, you know, since decay, you can get an eigenvalue of the bigger one. We have used all of those things in some form or another. I'm not claiming any of those things are, you see. Okay. Now, that lemma will deal what I do with good boxes. And first, I mean, we made sure it worked if you only had good boxes, but when you do a multi-scale analysis, you know if your probabilities are going to propagate, you have to have some bad boxes. Otherwise, there is no free lunch, right? Okay, so if I have boxes that are not localizing, what do? We are going to surround them with a buffer of localizing boxes, and we are only going to study eigensystem, not for the bad boxes, but for the bigger system. So I have to define a buffered box. Okay. I have to define a buffered box. So epsilon in lambda L is a buffered subset, not a box. First is a connected set in the form. It's a union of boxes, intersected these boxes, and it's connected, so they intersected. And so this is not my, I assume it's level spacing. By the probability estimate we have, this is basically free. And there exists a collection of points such that for all of those points, the box of size little l is M-localizing. And for every point in the internal boundary, I can find a point here such that y is actually in the core of this box with respect to gamma. Let me actually explain, because easy. let me do it. Suppose I had the buffer was a box. What this is stating is that I take a point in the internal boundary. Then I can have a box like that. And look what's the statement here. 2L theta, but with respect to upsilon, which means that that's the only thing I'm taking out because there is no boundary here. That means that for every point here, that means that y, which means this point here, is not close from the boundary in the box upsilon itself. So I cover by things that are good, and then I take upsilon check to be the union, oh God, of these good localizing boxes. With the tau means that I just take the core, the internal core, and then when I switch from a check to a hat, it just means I take what's inside. And now the lemma now is that I take a buffered subset and take an eigensystem. I can do it, level spacing. Now I define sigma of G of H gamma to be the union of all the eigenvalues in H of H gamma that I get from the good boxes, from the core of the good boxes, and sigma bad is what is left. Then for all new in sigma bad, we can show that the corresponding eigenfunctions decay if you are on, and we are going to have basically, that will mean this set here. So by the constructions, these eigenfunctions of the eigenvalues in the bad spectrum decay roughly in the boundary of this box. And if I now assume that lambda L is actually level spacing and take an eigensystem for it, we can now show by the previous argument that if I take these in a bad box, this also maps one-to-one, an injection, into nu tilde, which is an eigenvalue of the bigger box, but it did not come from the good boxes, and nu tilde minus nu is also close together, and again, the aligning the eigenfunctions are also not far apart. So we basically get almost not quite the same statement as for good boxes, except you don't have decay, you just know things are close. Okay, and okay, one more definition. I call, what is this? Sigma epsilon of lambda L to be all the collections of the nu tildes that I got from the bad spectrum of the buffered subset, which I know is contained in these, and it's not, didn't come from the good boxes either. Now, the mood-scale analysis, that's the induction step. For some scale, for M, I give that the localizing is good probability. Then I say if it is sufficiently large, the probability for capital L is propagates, little l, big L, and M, we just lost a little bit. In the end, those things are summable and they'll be less than a half. I mean, so that's why you get M bigger than M0 over 2. Okay, so so that's really the mood scale analysis, the heart of the mood scale analysis. And how do we do it? Well, we cover the box by boxes lambda L. So let me just say, you have to, these are not new arguments. So I have the box, bigger box, and I cover, but I cover with boxes that have a certain overlap, okay? And cover exactly. Rho is chosen. These are not important here. They have been important in previous work, but they are good enough, so I didn't. I do it, I chose row, so this is actually exact, and all the centers of the form x0 per row L times the number in ZD, but I only take something that's close enough to x0 to be in the box, and that's why we really need to consider boxes centered in ZD. And then let me say the event that I have at most n disjoint boxes of size little l in the cover that are not M localizing. If you take n to be L gamma minus 1 zeta tilde, the probability of the complementary event is small. That's not a new argument with the same things I had it in the work with Germania for the bootstrap with scale analysis. The same thing. So this is not. Now, I'm going too fast. Fix omega in this and take the less than equals to n possibly non-localizing box, and I put it inside subsets gamma r, which are satisfy all the requirement to be a buffer subset, except that we don't know that if gamma r is level spacing. That is like you do with usually in the usual multiscale analysis. We don't know if you have a Wagner estimate or not, but you know that there are some boxes here, there is a certain number, and anything that doesn't intersect with them is good, so you make them a bit thicker, so everything centered outside is good, and you can play with it, and you can show that you can actually put good boxes around them because I isolated them, and they have everything to be buffered except that they are not level spacing. So if I take the events that's a box and all the possible choices, because I know basically what are the possibilities, are all level spacing, I can estimate the probability. This is just a combinatorial, I'm not going to go into it. You get, because this is a dominant factor, this comes from that estimate with Molchanov, we get 1/2 a to minus 8. So if you define this event, it follows that this event has this probability. Now, what you have to do is to prove that for something this event, we have a localizing, the box is localizing. Now, so I fix here, this is true in general, it came from lambda L actually, because of the way I constructed the cover, is a union of thick core, deep inside cores of the good boxes, plus of the insides of the buffer boxes, of the buffer subsets. I can divide my boxes. This comes from the geometric construction, where G is a set where these are M localizing, those are the buffering subset. My construction gives me that. And now, I like sigma G, all of those, all the eigenvalues I get from the good box, and all the eigenvalues I get from the bad part of the buffered boxes. And now, and Alex is going to talk about it, it's important to prove that if you take both of them, we get everything. All eigenvalues of H in the big box comes either from good boxes in the lower scale or comes from the buffered boxes in the lower scale. But we get everything. That's crucial. That means we got what we want. Now we want to index eigenvalues and eigenvectors by sites in omega L, and we are going to use Hall's marriage theorem, which I'm going to state now. It's a necessary and sufficient condition for the existence of a perfect matching in a bipartite graph. And so let me just state Hall's marriage theorem that you can find in textbooks, or you can just Google it. Let G, A, B be a bipartite graph, which means I have A and B are vertices, E are edges, but the edges have one point in A and one point in B. That's a bipartite condition. A collection of bonds or edges is called a matching if every vertex of G coincides with at most one edge from M. So you cannot have any from every point, or either A or B, you only have one, at most one edge. It is a perfect matching if every vertex of G coincides with exactly one edge. Every vertex is matched. In other words, the bond gives a one-to-one map from A to B. Clearly, if you are going to have a perfect matching, you must have as many points in A as you have in B. So that's a necessary condition. And given a vertex A, let me call n of A to be B in B, A, B in E. This is usually called in the literature the friends of A. All the points in B that are connected to A, the set of neighbors, or called neighbors, but and now for an arbitrary subset of A, the neighbors of U are the unions of the neighbors of the individual points. Howe's marriage theorem says the following: consider a bipartite graph with size of A equals size of B. There exists a perfect matching in G if and only if the graph satisfies Howe's condition. And Howe's condition just means that the number of neighbors of a set is always bigger than the number of points in the set, but this has to be true for all sets. So if you can establish this condition, you can get a matching. So let's apply it now. Our bipartite graph would be the sites in lambda L, the spectrum of H lambda L, and I have to tell you what's the edge set. And that's where the work goes. For each lambda, I pick one in the good, that came from the good boxes, I pick one eigenvalue in one good boxes that goes into that. Doesn't matter which, just for each one I pick one, and I set n0 to be all lambda coming from good boxes such that x lambda minus x is close enough to x, close enough. And this is only done if I am outside the inside of the buffered boxes. And this is empty set if I am inside buffered boxes. And now I define n of x to be n0 of x if I am away of the buffered box, of the inside of the buffered boxes. It will just be the eigenvalues coming from the bad part of the spectrum of the buffered boxes if I'm inside the buffered box. And if I am basically in the boundary between a buffered box and the good part of the box, and the good boxes, I take both. And now I set bounds is that x lambda is here if lambda is actually a neighbor of x. Although it may not be clear, this was really defined to make sure that psi of lambda x is very small if lambda is not in n of x. You have to prove it. I like to talk about this. We then set n of theta, that the definition is the union of the neighbors. Oops. Okay. And this, of course, is true, obviously, the way we have done it. And to apply Mau's marriage theorem, we actually verify this condition. You have to prove that the number of neighbors of theta is bigger than the number of points in theta. Once you have that, we can apply Howe's marriage theorem, and we conclude that there exists a bijection from here to lambda x to points in the spectrum where lambda x is actually one of the neighbors. So I basically know where they are. And we set psi of x to be psi lambda x for all x in lambda L. And to finish the proof, we have to show that what we got is an M-localized system. Okay, very quickly, we fix x and take y such that the distance is of certain order, so we cannot have a problem. If y is in the good part of the spectrum, lambda x is not coming from a good box, so we can get this decay when we move. That one is the estimate you had before. If I happen to follow inside a bad box, a buffer set, this also cannot be here. This thing needs time to explain, so I can go also, this is small, but I don't have decay. So now we can just finish. We take x, y, we take it far apart like we want. We take it to be positive, otherwise nothing to prove. And we repeat what we did. There are only two possibilities. We accumulate decay. And the accumulate and decay, you can say how much decay can I gain. I can only move going from y to x, but I don't gain anything as I traverse the buffered boxes. And I also cannot get too close to x, so I lose a little bit. This is just to estimate. You can show this is equals to that when you took that, and you conclude you have a localized system so that the box is M localizing. Alex is going to explain to give more of the details. This is just a very fast overview of how we get there without using Green's function. Thank you.
Thank you.
So the completeness is just from basically the size of, once you have the matching, that gives you completeness, is that?
No, completeness we proved before. We proved completeness, you mean you get all eigenvalues, right?
Yeah.
We did that before. If you look, that was before we even got there. No. Although the argument is not too different from proving House condition. Okay? Here. No, one more. This is completeness. I get all eigenvalues that came from cores of good boxes, smaller good boxes, and all eigenvalues who come from deep inside the buffer subsets. And here I say I get everything. That's completeness. But that's not the indexing. Although the arguments are not totally different. There is an overlap here, so maybe one can do it in a different way. And then to actually fix it, we use the House marriage theorem, and then we index. But there actually, the way we do it, that separates things. And notice there is no, it's not perturbative argument. We don't do it by perturbation theory. We just basically show that we have these blackboards. The key thing is basically to say, how do you replace a resolvent identity? That is really the key question here. We took this big box. We covered it by smaller boxes, right? If I take a good small boxes, I show that each one of the eigenvalues here, if I am inside, goes into an eigenvalue of the bigger box. Since I have overlaps, I'm always inside, I'm in the core of something. So I get, then I have the bad boxes, and my bad boxes were done such that inside, things that are inside are small up here, so they also pinch and catch something. And then you have to prove, because you have bases on the little one, you have enough overlap, you get completeness. That's an important statement, that you get everything. It's don't have the Green's function, so you have to work with many different things at the same time. I mean, you can. On the other hand, at the end, we don't have to go back to from the Green's function to eigenfunctions or other things. The statements are all already in terms of the eigenfunction. It's amusing.
So in terms of the eigenfunctions for the infinite operator now, do you get actually now better estimates?
It's the same.
Like
It's the same.
uniform decay or so on?
Now you get Zule. You get Ule, I mean the uniformly in boxes with good probability, because a localized box has Ule. They all decay exactly the same around L times of L to the T. No, we don't. The infinite up to now, I have not seen anything in infinite volume that we get that's any different from before. I have to say that. Okay? Not claiming anything there.
Okay. Yeah, we should stop here in the interest of time. Let's thank.
Thank you.
short break and we'll resume in about 20 minutes.
Okay.